Hello, good morning, everyone. So I think yeah, we are right on time, so we can get started with this series of the fourth episode of the webinar series today. The focus of today's talk is simulating performance along battery lifetime from just a couple of cycles. And this is indeed the fourth talks of the week. And this is actually a nice follow-up with respect to what my colleagues have shown yesterday regarding the automated P2D and ECM parameterization of battery cells. So today I'm gonna cover on a slightly different topic, so how we can extend the performance estimation through AI methods and machine learning approaches in order to estimate battery lifetime. But yeah, prior to that, I will give you again very short intro to Sphere Energy and myself, and then dive deeper into the way we believe we can speed up battery development processes, along with more insights into our time series AI models for battery data and our products, Apex Battery Intelligence, and now we can leverage this for supporting multiple use cases. And at the end of the talk, I will show you a very quick demo prior to the Q&A session. All right, so just briefly about myself. So I'm Gianmarco Gabrieli and I'm leading the AI team at Sphere Energy. I hold a PhD in AI for scientific discovery, and my expertise lies mostly in machine learning methods applied to scientific and engineering data modalities. And currently, I'm sitting in the Zurich office of Sphere, where our competence AI competence center is. But our company is spread across four different locations. So we have our battery technology center close to Augsburg in Germany, our data science lab in Munich, and last but not least, our engineering hub in Paris. And the goal of our team is to solve the toughest technological challenges, mostly in the battery and engineering space, ranging from advanced data management solutions to artificial intelligence powered products, together with the smart data generation topic, which is extremely relevant for the battery use cases. So we are ISO and TSAX certified and have a proven track record for the battery cell development processes, together with our Apex operating system to provide AI tools to support the battery development and validation steps. And we do this thanks to our partnership with more than 50 reference clients across the Europe and the globe. So I'll start my talk going from exactly the talk that was given by our co-founders on Monday on what are the bottlenecks of today's standard validation processes. So nowadays, whenever we want to validate a battery cell, we tend to test the multiple operating conditions. And for these operating conditions, we test all possible combinations or tend to do so. And this means that the end of life estimation and a full battery cell validation process can take even up to 6 months or more prior to obtaining then the cell performance and validation results. Then the approach that we want to take here is to use AI methods in order to enhance such validation processes, so as to reduce the end of life estimation and have a full validation project run within weeks instead of months. And this is what we attempt to do by designing a smart test matrix with a testing of a finite set of operating conditions and combination of operating conditions, and simulating the remaining combination of operating conditions so as to provide the final self-performance validation with a minimal validation test. So how do we do that, and why the talk today is more on the AI and machine learning topic? We leverage what we call time series foundation models, and these are very well known to the literature and also to stakeholders in various use cases and domains. And I'm referring mostly to weather forecasting and sales forecasting. For these specific use cases, the use of these time series foundation models has proven to be disruptive. In the case of the weather forecasting, we can obtain performances that are above the traditional physics-based models. And in sales forecasting, we have seen the possibility of performing multi-horizon accurate predictions. So these time series foundation models are based on transformer-based architectures. We probably all know about the latest advances in generative AI in large language models as well as in image processing domain. So there's been a lot of effort in research to translate these methods to processing time series data. And this is exactly what we measure when we perform a test with a battery cell. So we obtain time series data from the physical measurement, and we use this in order to estimate or predict or forecast the behavior of the battery cell, similar to what we see in the weather and sales forecasting approaches. And again, research is quite fast on this topic. So we have seen in the past few years a lot of developments on the development of new architectures that are constantly being benchmarked and evaluated on the real world data and use cases. So we started indeed from evaluating all these architectures, and starting from this, we then created our own AI model, which again is an AI time series models for battery data, which is based on the transformer-based architecture. So it was designed by us to effectively process battery data. So what does this mean? So we say that our model is a multimodal input model. So it is able to process multiple input modalities at the same time. And this is not only the time series data, like the actual laboratory measurements and the measured data during operation, but also the design of the design information on the cell. So this is a categorical kind of input, comprising, for instance, the general information on the anode and cathode material, form factor, and all the base information that we will know about the cell. And we can use the model that is prompt with this kind of multimodal input to predict multiple key performance indicators at any point in time in the future. This means that if we prompt our model to predict each and every point, the future of the battery, we can ultimately estimate its end of life. And we have benchmarked directly our model and our architecture with respect to the other time series foundation models, which again were developed for a variety of use cases. So the same architecture can be used to address multiple use cases. And we have seen that when benchmarking our model with 10 extensive data sets comprising cycling data under various operating conditions, meaning varying temperature, C rate, and also exploring the inter and intracell variability. We have seen the model outperforming the foundation model architectures like TimeXR, dLinear, and HATCH-ST, both on the mean absolute percentage error as well as the percent correlation coefficient between the actual behavior of the cells and the predicted values of the lifetime of the cell. So how do we actually envision to use this model to go from the test data to the AI-assisted simulation? So here I'm going to show exactly how this approach and what I'm presenting today is a nice new piece of the puzzle with respect to what my colleagues have introduced in the past days within the other webinars. So the foundation is always the same, and of course, it is of paramount importance for any data-driven method. which is the data that we use to, let's say, train or calibrate our models and systems. So we always start from an initial testing campaign with various characterization techniques. We can harmonize and pre-process this data. And as my colleagues have shown on Tuesday, Nico and Victor, we can harmonize and visualize this data in a way that it is easy also to retrieve and obtain the most relevant key performance indicators. And we use this data in order to create what we call the battery digital twin. So a battery digital twin is meant to be a digital replica of the battery cell, so that in practice, whenever either there is new measurement done with that cell, or whenever the user triggers a scenario simulation, the digital twin can be used then to estimate the lifetime under the scenario that was asked by the user. And we can visualize the results and benchmark with respect to all the other cells that we have tested. So this is the overall pipeline, but I want to give you a little bit more insights into how this is done in practice on the battery digital twin generation. And this is also merging the model architecture that I've presented earlier. So we have a specific flow going from the measurement data to the actual test done by the user. So in our pre-training stage, which was already conducted by us, we pre-train our time series AI models with various data sources, and I will give you more details about this later on. Combining both, again, design data and cycling data. And we have used this model in order to create what we call the cell digital representation. The cell digital representation is then supported or complemented by a physics-based model, which is simply automated, parameterized, thanks to the approaches that my colleagues Kais and Lawrence showed yesterday. And we use indeed this model to enrich the cell digital representation. So this is a fixed and base battery digital twin that is valid for all the battery cells that we want to test. But then that comes the moment of the fine-tuning of the digital twin with a new device under test or test type for a specific user. So whenever we collaborate with our clients and partners, what we do is always starting from the base models that is always the same, and then we fine-tune it to make it private to that specific user, so that the model has a little bit even more knowledge about the kind of test or the kind of cells that are tested by the user. And this means that at inference time, the user himself has at his disposal the battery digital twin, and by providing beginning of life data or again the simulation scenario, it is possible simultaneously to simulate the aging behavior until end of life, as well as unveiling the aging mechanism thanks to the physics model backbone, which has been part of the pre-training phase of our model. And again, stressing on this topic, we have seen a lot of efforts recently in machine learning and AI to support AI-assisted prediction with explanation methods, and explainability and uncertainty quantification are very hot topics in the research community. So the physics-based model that is used to complement the cell digital representation is actually also used for this purpose. So we obtain from our battery digital twin not only the simulation, but also the losses mechanism underneath the aging mechanism. And this is on the explanation side of our modeling approach. And again, I hinted earlier at the fact that we pre-train our model ourselves on our own data sets. And these data sets, to give you more insights, are based on two main sources. So we have a synthetic data set comprising more than 10 billion battery simulations, ranging a wide variety of nominal cell capacity, good distribution of the cathode materials, distribution of test temperatures, as well as SOC windows. And we complemented this base synthetic data set with actual experimental data set recorded in our facilities in Augsburg. And this also comprise an high distribution of cathode materials as well as large distribution of temperatures. And this data set comprises more than 4K experiments, which is a nice and complementary real data set, so real tests with respect to the synthetic data that we use to pre-train our models. So this idea of using the battery digital twin to support battery validation process is, as I said, a nice follow-up to also what we mentioned we can do with our automated P2D and ECM parameterization that my colleagues have explained yesterday. So while on one side the Apex sphere framework is able to estimate the performance of the battery at any point in time, and this was the focus of yesterday's webinar. Today, I'm mostly focusing on the aging simulation, so how we can use the machine learning methods to reduce the number of experiments in the design of experiment matrix, and how we can replace the classical DOE with the AI-assisted DOE. And we have started this investigation by looking into various data sets that we had tested in our testing center and realized how there are multiple variables that are interleaved and can be impacting the performance of the battery cell at the same time. So we want to, as I mentioned, reduce such design of experiments thanks to the AI-assisted simulation. So we have run various studies in which we can inform the design of experiments to then effectively use our models. And on a study run on our benchmarking data sets, we have estimated that we can confidently reduce the test matrix of about 30% without losing any accuracy in predicting the behavior of the cell or estimating the behavior of the cell. So with a 30% test reduction, we were able to recover the curves of the lifetime of the batteries with an error below 1% and as-per coefficient of determination value above 0.95. But of course, it is possible also to reduce further the test matrices, of course, at the cost of a slight increase into the prediction error. So we have tested this also with 50% test reduction as well as the 70% test reduction. And we have seen that the more tests we remove, of course, the higher will be the uncertainty here. But going then deeper into two specific use cases that we usually address and try to solve with our clients, we have, and I mentioned this multiple times at the beginning of the talk, the possibility to use our Apex model to simulate different temperature and C rates. So let's say the missing data points in the design of experiments. And for doing so, we use at the fine-tuning stage limited data from our tests, and we run what we call an intra-cell extrapolation. So within the same cell chemistry that we use also to fine-tune our models, can we predict the remaining operating conditions? And we have run this study again on various data sets, and I'm here reporting a general result on an open access data set where we have a varying C rate and temperature. And when cutting the design of experiments of 50%, we were able, as I mentioned, to obtain a mean absolute percentage error below 4%. So this was satisfactory for the reconstruction of the end of life of our battery cells. But this is not the only use case that we address. As I mentioned, we go beyond the intracell extrapolation to the intercell extrapolation. So whenever there is a new battery cell that needs to be validated, we have the possibility to fine-tune the model with similar battery cells that were tested already by our clients or by us, and use then the digital twin in order to estimate the end of life of this new battery cell. And as a very short example here, I show how we kept out of our pre-training and fine-tuning data sets these two cells, the Molicel P45B cell as well as the LGM50T cell. And we have validated the possibility to simulate the end of life of both cells just by using as fine-tuning all the other cells that we had available in our training data sets. Okay, so I hope by now I convinced you that with our Apex model, we can indeed accelerate the battery development process. And this is combining both the approaches that were mentioned yesterday by my colleagues on the accelerated parameterization with Apex physics. So we estimated we can reduce the calibration effort of more than 60%. We can confidently reduce the design of experiment matrices for battery cell validation of about 30%. And these two metrics combined together have led us to estimate the possibility to have faster cell benchmarking of about 2x. So now, before going to actually the Q&A session, I would like to maybe go through a quick demo with all of you just to show you how the tool can be used or could be used in practice. So I'll quickly switch to the other tab. Okay. Perfect. So we see here in this tab the set of digital twins that we have calibrated in this case. And again, this is just for the sake of the demo. We reported a few cells that we tested, but we have plenty more in our pre-training data sets. And for each of these cells, again, we can visualize a set of let's say, general chemical information about the cell. So what is the chemistry, general form factor or dimension information, as well as some of the electrochemical parameters that were estimated for the cell. And we have available all the cell measurements that were performed in our database. And as you see, the status can be different depending on whether the test was already used to fine-tune our model, whether the test was actually coming out of the AI-assisted simulation, but also if there is new test data, test measurements being done for this cell, we also can visualize this in our digital twin overview. And of course, whenever there is new data for that specific cell, we can further refine the digital twin with the new battery data. This is a very important step to augment the knowledge of the model. And once the digital twin is ready, we can then use this for predicting performances of the cell. So again, here in this example, I show the possibility to select a battery model from the digital twin library. So you can select any of the digital twins that you have, and then you can build your simulation scenario. So starting from custom simulation in which you can ask for specific temperature, SOC ranges, and C rates to extensive design of experiments simulated with the digital twin. So this can be a standard cycling aging DOE, an extensive design of experiments, or even like a minimal set. This is indeed what I'm gonna show you for the sake of time. So whenever we press the run simulation button, what's happening here is that the model, the digital twin, is prompted with the different operating condition of interest. So the combination of temperature, SOC range, and C rate. And at the end of the simulation, which is tracked by this log. We would see the results of the simulation in the next tab here, where we can visualize and compare seamlessly all the degradation curve that we see, both in terms of temperature and sea rate, but we can swap the axis with the visualization on what will change with the different SOC range, and again for different sea rate. Now, for each of our prediction, we can also estimate the degradation mechanism. As I mentioned, this comes right out of the physics-based model component of our approach. And of course, we can, at any point in time, visualize our simulation compares with respect to the reference performance test actually performed with that cell aged under the operating condition under test. So this is nicely, again, coupled also with our data management platform where we can select any of the tests that were done. And again, here I just included a finite set of such cells. And whenever we select one or more of these cells, we can add to the visualization pane. This is exactly what is showing here, and actually make the prediction on the spot for the different cell or measurements that we are actually running until a certain point. So for these specific cells, we have tested 50 cycles, but we can predict the behavior for the remaining cycles. So this is possible and is triggering exactly the same model. Of course, in this case, it is a little bit faster because there are only two tests being estimated here until the end of life. All right, so this is the last was the last part of the demo. So I think next we can go to the Q&A session. So I'll stop sharing my screen and take a look at the questions. Yeah, I'm just gonna read. Uh, Perfect. Yeah, so I'll start by this, which is how can your AI help to predict calendaric aging? The availability of trustworthy years of testing historic data is usually poor. So this is a very interesting question because so far and within the presentation, I've shown mostly the let's say cycle aging behavior, but less about the calendaric aging. We have tested also the possibility to estimate the calendaric aging degradation. There has been a few open access data sets as well as some of the data that we have in our facility on calendaric aging. So we have also validated the possibility to estimate the behavior under the different, let's say, calendaric aging conditions. So yeah, if there is any interest in exploring this, we are very happy to provide more insights. Yeah, I see then another question. How do you get the specific aging capacity losses when doing an AI aging simulation? If the AI aging simulation is fast, you won't do physical simulation. So the capacity lost by ACI, cracking, and so on. Um, Exactly. So how sure are you about the validity of attributing aging capacity loss to specific processes? Okay, this is a super interesting question. So again, and as you mentioned in your question, we have used a physics-based model to pre-train our models, so to extend the cell digital representation. What we do at the inference stage, right? So when we use then our model being pre-trained or fine-tuned in whatever sort of form to estimate the behavior of the cell, we actually also estimate the aging phenomenon and aging parameters directly thanks to the part of the cell digital representation that is associated with the losses mechanism. So in order to validate whether our approach will work, so whether the embedding or cell representation of the physical level would match the aging mechanism. We validated the predicted or estimated capacity loss from the physical model cell digital representation with respect to physical models estimated from scratch. So this was exactly the topic of yesterday's webinar, where we showed how we can perform automated parameterization of such models. So we validated those loss mechanisms with respect to the output of our AI models. Okay, so I see a few more questions. Say you have a new cell for aging prediction. We have a few cycle of aging data. What more information do you require to use your model? Yeah, so this I think this question is about, how much the new cell can be a new cell or similar to what we have seen before in our pre-training data. So the kind of information that we will need to have in addition to the cycle aging is base design information. And this can be, as I mentioned before, like the anode material, the cathode material, what is the nominal capacity of the cell, the form factor, the geometry. This has been taken into account by our pre-trained model. So this is the base information that we would like to have. But of course, if there are even more informations also on the electrolyte being used and so on, this can be used for better parameterization of the physics-based model to enrich the cell digital representation. Okay, does the training data set include the real field data which contains noise? Yeah, this is very, very important question. So I think, yeah, the focus of today's talk has been mostly about, validating battery cells as it is usually done in testing center, following specific protocols and under predefined conditions. Of course, as I mentioned, we have our data harmonization and processing platform that filters out the non-relevant or noisy data from the testing measurements. But then if the data comes from the field, so let's say an installation of the battery in a battery cell, we have, let's say, slightly different use cases with respect to the one that we have mentioned today. And yeah, please feel free to reach out about the field data topic. This goes more into our solution for SOH estimation and SOC estimation in the field. Okay, I see a few more questions. There are so many bumps in your AI output prediction of aging, especially the LGM50T. I may predict the correct trend. However, I think it's weird that if these bumps were to be seen in a physical simulation, everyone will be skeptical about the results. How are you planning to address that? Very important question. So, in the prediction of the specific cell that we have shown, we indeed realized that, of course, that cell was very similar to other cells that we had in our pre-training data, in which the recovery time of the cell after a reference performance test was quite long. So, since the test was done, since the tests were done at different temperature or different C rates, it can be, of course, that the recovery time is very long. So we see all this behavior with the bumps also in the training data. But this is real data, right? So this is exactly how the test is done with the cycler under that operating condition. So the prediction of the bump itself comes from the attempt of the model of reconstructing a real history of the battery cell. So, and as I mentioned, since the model is primarily data-driven, of course, this kind of behavior can occur, while, if we would have to use purely a physics-based model, this would not have been the case. Yeah, what is the accuracy of the fine-tuned models and RMC on the cell level? This would provide more insight about the fine-tuned model, its performance. Yeah, so we will provide right after the webinar more, let's say, a summary of what I've described, and you will see even more metrics displayed there on the different use cases. So yeah, in the presentation, I show mostly the mean absolute percentage error and coefficient of determination, but we will provide also this additional metric. Why do you think your AI model performed better than the other time series phase architecture? Yeah, as I mentioned, our strength was in developing this architecture that would combine simultaneously both the time series data as well as the design information seamlessly together in a multimodal input fashion. And this is something that, thanks to our battery expertise, we could do in an effective way and, let's say, infuse the domain expertise with respect to what is public knowledge, of course, on the time series foundation model. Yeah, for degradation mechanism loss estimation, do we need any specific test experiments? Yeah, so since for this we use the part of the cell digital representation using also the physics-based model, we believe that, of course, the characterization data like pseudo OCV or impedance spectroscopy at beginning of life will be enough to have the parameterization of the physical model in place to enrich the cell digital representation. So this is usually the kind of test that we have. Mostly, yeah, the OCV EIS is desired but not required. But of course, any additional characterization that is usually done, like C-rate test or pulse charges, this is also helpful for the model. Yeah, I see also one more question about yeah, somebody that was a little late to join. Again, on the kind of inputs that are using for the model and the kind of cell chemistries that we used, we are very happy to provide this information as yeah, follow up to the webinar. So you will see all the presentation again as well as the summary for you. All right. Yeah, I think this was the last question. Maybe share my contacts here again. So, yeah. Indeed. So if you have any questions and you want to know more, know how to get access to our model and how to engage in a collaboration with us, please feel free to contact me. Again, my name is Gianmarco. This is my email. But of course, as we mentioned in the chat, you can also reach out directly to the info@sphereenergy.eu. And very important, tomorrow there is the last webinar of this series on another very, very important topic, which is on the trusted AI. So how we can infuse, let's say, the trustworthiness in our models, and also how to estimate the uncertainty for our prediction. All right, so with this, I will stop sharing the screen. Thanks a lot for your attention, and looking forward to receiving your follow-up questions to our communication channel.